Bhadrakali, the sitting goddess of Bhadrak. With her name, the Bhadrak is named Bhadrakali. And sir, I invite you for Veda Patha, and will share the screen.
Good morning to all. At the outset, I offer my humble pranam at the lotus feet of Lord Jagannath and Ma Bhadrakali. Now, lighting of the lamp. Asato ma sadgamaya tamaso ma jyotirgamaya mrityorma amrutangamaya. Om Shanti Shanti Shanti. Ganapati Pratha. Om Gananam Tva Ganapati Havaamahe Kavim Kavinam Upamasravastamam Jyeshthārajam Brahmanam Brahmanaspatanas Sannannoti Bhesida Sadhanam Prano Devi Saraswati Vaje Bhirvajini Dhinam Avitriyavatu Ganeshaya Namaha Saraswati Namaha Sri Gurubhyo Namaha Harihi Om. Ganapati Atharva Sirsha. Om Bhadram Karne Vishunuyam Devaha Bhadram Pasye Makhya Virya Yatraha Stirangai Stustu Bhagam Sastanobhe Vyasema Deva Hitam Yadayo Swasti na Indra Vruddhasavaha Swasti na Posa Vishwavedaha Swasti na Starkyo Arishtane Mehi Swasti na Bruhaspatir Dadhatu. Om Shanti Shanti Shanti. Om Sarva Mangala Mangalye Shiva Sarvartha Sadhike Saranye Trambake Gauri Narayane Namastute Nilachala Nivasaya Nityaya Paramatmane Balabhadra Suvatrabhyam Jagannathaya Te Namaha. Swasti Prajabhya Paripalayantam Nyayena Margena Mahim Mahisha Go Brahmanebhya Subhamastu Nityam Samasta Lokaha Sukhino Bhavanto Samasta Lokaha Sukhino Bhavanto Samasta Lokaha Sukhino Bhavanto. Om Shanti Shanti Shanti. Next.
Thank you, sir. Now, according to our program schedule, Principal Sir will give his welcome address. So, I request our Principal Sir to deliver his welcome speech and welcome our audience today. Sir.
Sarve bhavantu sukhina, sarve santu niramaya, sarve bhadrani pasyantu, ma kaschit dukhavad bhavet. Very good morning to all. First of all, I welcome respected Sir Ananta Prasad Chakrabarti, Assistant Professor in Physics, Gangadhar Meher University, Sambalpur. I am happy that he belongs to our Bhadrak locality. He is very talented and eloquent speaker. I welcome all the participants, such as teachers, students of different colleges of our state. I am thankful to Mr. Sridhar Pandasa, Reader and HOD of Physics, for organizing such a webinar, which is very helpful to our students and teachers of both physics and chemistry in this COVID-19 pandemic. I am also thankful to Dr. Sukanti Mahapatra, lecturer in English, and IQAC coordinator, who helped a lot for arrangement of such webinar. About the topic, I can say material science is an interdisciplinary field involving the properties of matter and its applications to various areas of science and engineering. It includes elements of applied physics and chemistry, as well as chemical, mechanical, civil and electrical engineering. In general, materials that widely used in this universe are divided into four types: metal, polymers, ceramic, and composites. There, there are plenty of manufacturing processes that have been developed to form a product. Friends, as a teacher of botany, I have little knowledge about the topic. I hope our respected guest, Ananta Prasad Chakrabarti, will enlighten us, and I am sure students will be benefited by this webinar. Thank you. Over to Sridhar Panda sir.
Thank you, sir. Respected principal, sir. Respected IQAC coordinator, Dr. Sukandi Madam. Honorable resource persons, Dr. Ananta Prasad Chakrabarti, sir. Esteemed colleagues, dear students. I, Sridhar Panda, HOD in Physics, extend my warm welcome to all participants and dignitaries to our webinar on the topics emerging trends of research in material science, an emphasis on polymer composites. At the outset, I would like to say something about our department. Since honors classes opened in 2003, I have been in the department through ups and downs. In spite of all the constraints, our students never failed to achieve success in life. Most of the students are engaged in different sectors like banking, defense, software, and also in education line. One of our students has completed PhD after qualifying GATE and engaged in a government college. Recently, one student qualified GATE completing MSc in physics. Some students are now continuing MSc in physics in different universities all over India. They are pride of our department. Now, I feel proud to introduce our honorable resource person, Dr. Ananta Prasad Chakrabarti. He is a son of this soil, that is from Bhadrak of Bhadrak district. He has got his BSc Physics honors from Fakir-Mohon University in 2004 and being awarded as a gold medal of a best graduate among all students across the university. He got his MSc Physics from Ravenshaw Auto College, Cuttack, affiliated to Utkal University in 2006. In January 2011, he has got Master of Technology in Metallurgical and Material Engineering from NIT Rourkela. He joined as PhD student in NIT Rourkela in 2011. Finally, he has been awarded with the degree of Doctor of Philosophy in 2015. He has published 20 research papers in reputed international journals and conference proceedings. He has published a book in Lombard, an international publisher. He has been awarded with so many state and national awards. He has also got Nalinikanta Swami Memorial Award for being best performing students in Department of Physics, Ravenshaw Auto College, Cuttack. He has around 7 years of UG and PG teaching experience with so many departmental and administrative responsibilities. He has served as assistant professor in C.V. Raman College of Engineering, Bhubaneswar, recently known as C.V. Raman Global University from 2009 to 2011 and 2015 to 2020. Currently, he is working as assistant professor in School of Physics, Gangadhar Mehra University, Sambalpur. His research areas belongs to composite materials, polymer composites, glass fiber, reinforced polymer composites, environmental sustainability of FRP composite, carbon-based nanopolymer composites, green composites, waste utilization, characterization of materials, etc. Today, he will give a webinar talk on details of materials in recent days scenario and their recent research trend. He will also extend his talk on his research expertise on polymer composites. It is an honor for us to listen to him today. Now, I request to our resource person, sir, to enlighten our students and participants. Sir.
Thank you, sir, for such a introduction. I belongs to BHADRAK. It is a proud moment for me, and my schoolings and my college days are also from BHADRAK College. Though it was affiliated to Fakirman University on that days, now also, but all such things are from BHADRAK. As we know that BHADRAK is famous for Bhadrakali temple. It is just 1 kilometer from my residence at BHADRAK. My village is Aharpada, from that 1 kilometer distance, and Akhandalamani temple at Aradi. And actually I proud to be from BHADRAK. Now, day by day, I have visited so many institutes for my academic degree, but by the meantime, I have never forgotten my motherland, my alma mater, BHADRAK Autonomous College, and it is actually a proud moment for me to contribute myself, my expertise for all our participants and listeners, and invite them for collaborations. So let me to share my slides from this Google Meet. Is my screen available to all? Madam, Sukanti madam?
No, sir.
Yes, sir. Yes, sir. It is available.
So,
yes, you just start. It is available. Yeah.
So this is the webinar talk that is emerging trend of research in material science and emphasis on polymer composites. I may focus the students across all disciplines, because material is the thing that everyone should know about it. Whenever you will start anything else for any purpose, you will start with some materials. So it is not for science students, but for the students of all disciplines, so they may listen. And the part 2 is the emphasis on polymer composites. That will be for physics students or chemistry students, botany, zoology, or those interdisciplinary students of science. They may listen it. So now, this is the Gangadhar Mir University, the place, the academic I belongs to, and this university is named after the famous poet Sobhab Kavi Gangadhar Meher, and his written poem Vishwa Dekha Madhu Mayore Jivana. That poem was the university anthem for us, and this is the faculties just stood behind all the administrative peoples, and it is the second convocation ceremony. The photograph was taken, all the faculty members of School of Physics, Gangadhar Mir University. So now let us start, let us begin the today's topic, the emerging trend of research in material science. First of all, I must focus on material science and different classes of materials. And basically, I have focused for the students, the graduating students. So first, let us begin with materials. What is actually materials? So already I have told, anything will begin with any kind of things. You have to first search for a material. First, you have to choose your material. Then you have to select what design you have to give. So hence, material is the first criteria, the first thing for us, for which we must go with. So in any kind of things, you have to, whether it may be electronic, electrical, civil, infrastructure, or any kind of things, you have to go for a material. Now, what materials you have to consider for different applications? What material? First of all, you have to know what is its design criteria. In what applications you have to use it. You have to choose it. Then what property we need? Let us consider we have to construct a building. Then that roof must sustain that what amount of load or what amount of sustainability. So considering that one, you have to choose your that classes of materials. Then the duration. It is important. The duration you have to consider. The up to what duration you want, and safety factor. It is a very crucial parameter, and environmental issues. That in different environmental aspects like different humidity, the high temperatures or high to low temperatures or low to high temperatures, that material will sustain or not. So keeping this in mind, you have to think that what material I have to consider for which applications. Then basic concepts of materials, it originated from the word matter. Matter, it is the substance or the mixture or the substance that constitutes an object, and it may from living or non-living matters. And materials can be classified with respect to their different physical or chemical properties or geological origin or their biological function, different with respect to different properties or their different appearance or their different availability. You can classify the materials. So the study of material is known as material science, and when you use these materials in different devices, that branch is known as materials engineering. So basically there is no such difference between materials engineering and material science. I have given a clear-cut figure that in an aerospace body, in an aeroplane, that how much parts of titanium is used, aluminum is used, steel is used, and other classes of materials are used. So keeping the different applications in their mind. So now we should classify the matter first. Then we have to go for materials. The matter may be classified with respect to their physical classifications like solids, liquids, gases. And basically I must focus on the solids materials. Basically materials, we should focus on solid materials. And liquids and gases, these are no doubts are materials, but I have not focused in my presentations. And solids may be classified with respect to crystalline and amorphous, and with respect to chemical classifications, the materials may be classified as mixtures, pure substances. That mixtures may be homogeneous or heterogeneous, and in different classes of elements you may classify metal, non-metals, polymer, ceramics, etc. Different things, as our principal sir has already elaborated for that one. So now let us classify the materials in a broad aspect. In a broad aspect, you may classify materials will be from polymers, metals, and ceramics. Polymers are generally amorphous in nature. What is amorphous? In the forthcoming slides, I will explain you what are those. And metals are crystallines, and ceramics is the aggregate of it, is the mixture of amorphous and crystalline. When you will mix all the three things in their required proportions or in your specifications, whether the 3 or 2 of that phases will be mixed, so you may reach with the composites, and those composites have better properties than these conventional polymers or metals or ceramics. Now, what is metals? Metals are generally crystalline in nature. In this case, the lattice arrangements are purely periodic in nature. What are those lattice arrangements? That all the atoms will arrange in a periodic fashion, in a periodic arrangement. Those are known as lattice. Lattice are of different types. I'm not going in the deeper in the things. Those are actually in your courses of studies, or you may go for any book. Okay, and in polycrystallines, that those lattice arrangement, different lattice arrangements we can see. But in crystalline, one type of lattice arrangements we can see. But in polycrystalline, different lattice arrangements, they will collide, they will be intermixed, so that different lattice arrangements have their own boundaries, and those boundaries are known as grain boundaries. The example is quartz. And in crystalline, the examples are sodium or any kind of metals you may take in that. And in amorphous, there is no such lattice arrangements, and all those atoms are cross-linked together to have a chain. That is known as polymers, or that polymers of different types of polymers we have, and liquid state polymers, solid state polymers also, and all sorts of polymers are there. Conducting polymers are also there, but the basic things inside it that they will be cross-linked to give their overall solidifications. Now, if we have in our mind to construct material trees, then all the branches will be their metal, ceramics, polymers, composites, and the sub branches of the metals will be of different metals like ferrous metals. These are originated from ferrous alloys like steels or cast irons. Similarly, another sub branch will be aluminum alloys and aluminum type kind of things, and copper alloys. Similarly, a different type of alloys, their sub branches and their leaves, and their properties also you can assign. Similarly, for ceramics, their sub branches will be engineering ceramics like your barium titanate, the alumina, and different kind of ceramics. Similarly, traditional ceramics like stone, porcelain, quartz, all those things will be in traditional ceramics. Similarly, polymers will be of thermosets, which generally cures permanently. Once it is cured, you cannot revert back to its original liquid state. Okay. Similarly, in thermoplastics, it is cured partially. When it is cured, you want its liquid state, then you will give some heat or give some temperature, it will be revert back to its original state. Similarly, elastomers, these are also the one branches of polymers. And keeping all mixing with the suitable combinations by some mixing rule, then we will reach with the material that is known as composites. That when you will keep the emphasis on metal, that is known as metal matrix composites. And when you will take the emphasis on polymers, polymers will be to a great extent, that will be polymer matrix composites. And in you will give the emphasis to ceramics, then those will be ceramic matrix composites. Basically, I will give the importance to polymer matrix composites at my part 2 of my presentations. Now let us come back some glimpse of some idea about different classes of materials. Let us start with metals. These are generally polished, fractured, and it have lustrous appearance. These have high thermal and electrical conductivity. These are generally ductile and have high strength. And generally in our day-to-day life, we are using metals. Okay. And typically these are crystalline arrangements. Examples already you can see in the slides: aluminum, iron, etc. But the basic problems with the metals, these exhibit catastrophic nature of failure. Catastrophic nature of failure means it fails instantly, and it do not give any warning. Okay, so that means during use you have to be very careful about it. Then it can corrode. Okay, and when you will just keep the metal in outside in some environments like iron, it having some corrosion property. Then in metals, the very big trouble is that the formation of cracks. It may crack. You cannot avoid the formation of cracks. Then extraction process from our minings, in pure metal we cannot get. We will get in form of ores, and it's a very difficult process to extract those metals. Mining processes are also very difficult. So keeping this in mind, the emerging trend of research, you have to mix different metals to form alloys for different applications like bronze, steels. All these are of different alloys. And improvement of polishability, it is important that polishability should be improved so that it can be used, and its fracture strength must be used so that no crack must not be formed. And improvement of fatigue property. What is fatigue? Fatigue is that whenever you are using a metal and giving some loads, then after a certain time you are unloading that one. The load is removed. Then this cycle you will just continue for so many number of times. after certain number of times, the metal will do not respond to this cycle, that loading and unloading, and at the end it will fail. That is known as fatigue. And that endurance limit, you must not cross its endurance limit. So mixing of metals to avoid corrosion, that is also emerging trend of research in metals. Similarly, it will come back to ceramics. These are generally the solid materials that comprising of inorganic compound of metal or metalloid, and these are of different natural ceramics like earthenware, porcelain, bricks, and ceramic bricks you are just using, and these are generally brittle in nature. It will break immediately. High Young's modulus, high strength, high corrosion resistance, it will never corrode, and high thermal resistance also. And for this reason, these ceramics are used in blast furnace applications, and low electrical conductivity. It is very low electrical conductivity, low thermal conductivity. Hence, in some furnace, and these ceramics parts are used so that it will have a perfect insulating purpose. So then amorphous and polycrystalline in nature. So different examples are silica, alumina, zirconia, silicon carbide. Here also you may face the problems of catastrophic nature of failure. It can break easily, formation of cracks. Then you have to avoid all those things by some research. Then you have to go for to mix up some metals with the ceramic so that ceramic can sustain. Then you have to avoid formation of connected cracks or interconnected cracks, and you have to improve its fracture strength, its toughness, and basically how these ceramics will be used in some biomaterials and for dental materials. These are basically related to biotechnology, and this botany and zoology people can research in this area. So these are some basic research area in ceramics. Now the polymers. Polymers are generally consisting of very large molecules or macromolecules composed of many repeating subunits. These are generally amorphous in nature, and these are having low thermal resistance, low thermal conductivity, and these are thermosetting and thermoplastic in nature. So, and it requires some curing agent or some hardener for its curing or for its hardening. Okay, and you can see a picture where the engineer is giving some polymer coating on a ceramic pipe so that cracks should not form. Okay, that means polymers coatings are given to avoid the cracks. Now advantages with polymers, these are very good adhesives. These are also very good coating materials, and you can process polymers easily. You can apply anywhere else, like in a brush you can apply. Less maintenance cost, it will never corrode, and very high life cycles. So now disadvantages is that polymers generally absorb moisture, and moisture is the big detrimental factor for the polymers, and it swells, and with the process of hydrolysis it will degrade. These are having low elastic modulus, low glass transition temperature, which is generally known as the minimum surface temperature, after which the polymers generally plasticize and give plastic property, and its yield strength will be decreased, and its strength and everything else, its sustainability also decreased. Low processing time, crashing, and these are generally after curing or after hardening or after solidifications. These are generally breaks. It will give some high amount of loads. So you have to go for its design stress, up to what amount of stress or what amount of load you have to use it. So keeping this in mind, the emerging trend, you have to go for that how the moisture can be removed, or how we will design some polymers. It should absorb very low moisture content, having high mechanical property, conducting property, high glass transition temperature, and you have to mix some ceramics or metals in polymers to have some better composites for better properties, and those can be used in various structural and civil infrastructures applications. Now, if we classify those materials with respect to properties, and materials having different properties like dielectric properties, magnetic properties, semiconducting properties, superconducting properties, with respect to these properties, you can classify accordingly that dielectrics materials, magnetic materials, Semiconducting materials, superconducting materials, one by one I will give some glimpse about it. That now you can see some very eminent persons, very eminent scientists who have given their valuable time to reach with the various conclusions in electromagnetic induction. For diamagnetism and electrolysis, Michael Faraday has got the Nobel Prize. Similarly, Enrico Fermi for its radioactivity and Fermi-Dirac statistics. Similarly, Heike Kamerlinghe once for theory of superconductivity, James C. Maxwell for theory of electrodynamics, Charles Augustin de Coulomb for the famous Coulomb's law. High school students or school level of students know this, what is Coulomb's law, and Hendrik L. Lorentz for that also for Lorentz theory, and that is also the modifications of electromagnetic theory in relativity. They have given their valuable time to reach with, and for this we can classify the materials with respect to or using these theories. Now let us start with the dielectric materials. The dielectrics are so to say some insulators or electrical insulators, and whenever you will give some electric field that can be polarized, means that dipoles are oriented in a direction, in a proper directions. Okay, so that is known as your dielectric polarization. So with respect to different extent of dielectric polarizations, you can use these dielectrics in capacitor plates, and you can also change the capacitance by changing these dielectrics. Okay, and reduce possibility of shorting out by sparking during high voltages. So applications will be in that capacitors and the dielectric substances in transformers and in different applications. So now these are some different classes of materials having different dielectric constants, and as you know that a dielectric polarization vector P is epsilon 0 chi E electric vector E, and the chi E is the electric susceptibility, and the dielectric polarization should be greater for a dielectric substance, thus chi E should be greater. So chi E should be greater means epsilon R should be greater. That means a dielectric material should demand for greater dielectric constant. That dielectric constant must be and having low dielectric loss, and should have higher life for polarization, so that whenever you are using in a batteries, so that should be charged in the limited duration of time and must sustain for a higher duration time. So that should have, and should be smaller in size, so that in your mobile phone and some very small dimension of capacitors, it can be possible to incorporate inside it, and it should be cost effective with lower price. Obviously, we should reach with the cost effectiveness. So now you can see the dielectric materials, the markets of dielectric up to 2027. I have got this the report from this link that up to 2027 the dielectric markets has been already big filled, and in day by day this is prominently increasing how the dielectrics are so important materials, and why these classes of materials they play a crucial role in emerging research. Similarly, if we come back to magnetic materials can create permanent, temporary magnetic field. That may be ferromagnetic, permanent with strong, paramagnetic, permanent but weak, and diamagnetic, but it is temporary. So you can classify different classes of magnetic materials like ferromagnetic. Below critical temperatures, their spin vectors will be aligned parallel and in magnetic domains. But for antiferromagnetic, their spin vectors must be aligned antiparallel. And for ferrimagnetic, the spin vectors are aligned antiparallel but do not cancel. And in paramagnetic, spin vectors are randomly oriented. Keeping this in mind, you can use in different electromagnets, electric motors, transformers, and for data storage in magnetic tape, sensors, and superconducting magnets in fusion reactors. And hysteresis loop play a very crucial role for the magnetic materials. So whenever you start from the origin of that you have not applied in magnetic field, in the forthcoming time you will apply the magnetic field, then it will give a S-like of cycles, S-type of cycles. Okay, and the that C and D, that intercept in x-axis, that it will give you the limit of coercivity, and in the intercept in y-axis, that retentivity, that B and E, that will give you the retentivity. So the area of hysteresis loop, that signifies what magnetizations or what magnetic field strength should be imposed in it, so that you can know from its hysteresis loop. And this hysteresis loop can be predicted from different equipments, and these are having some emerging research trend, like you have to achieve the uniform magnetization at various temperatures, and critical temperatures must be improved, so that a magnetic material should be sustained up to very high temperatures. Particle size or grain size must be smaller with higher magnetic polarizations, and to prepare magnetic materials, the intermixture of various non-magnetic materials must be considered. How you have to prepare that mixtures, that is also emerging trend of research, and it is obviously a challenging aspect to prepare those sensors using magnetic materials. Now reach with the superconductors, and these superconductors are whenever you will cool this a normal conductor for some specific materials, not for all classes of conductors, for some specific materials like mercury, you will cool that after cooling beyond below 4.2 degree Kelvin, that its resistance will be decreased, the resistivity will be decreased, or zero resistivity property you can say, and in that from below that temperature, its conductivity will be higher, very infinite, and hence these are known as superconducting materials. These are exhibiting Meissner's effect, that means below critical temperature those excludes the magnetic field completely, and these are used in fusion magnets, power transmissions, superconducting sensors, etc. Now for these Bardeen, Cooper and Skipper, they have been awarded with the Nobel Prize for giving this superconducting theory, and well known as BCS theory. And I have already listed there are different classes of materials with different critical temperatures, different that up to how much temperatures you can use these superconductors, and these critical temperatures play a very crucial role. So unless until the superconductor is meaningless, you cannot use it. So emerging trend of research, you have to increase its critical temperature and its critical magnetic field, and its band gap, its forbidden gap must be smaller, so that that electronic transitions could be possible, and the fabrication process or the material synthesis process, how you can design or how you can synthesize those superconducting materials. Now reaching with semiconductors are generally with a certain limitation. These are not actually conductors, and these have some properties with respect to some electronic properties, that in band theory, for example silicon, that is higher orbitals 2s and 2p, their electronic arrangements, when we'll keep to at the atomic radius levels, the two silicon atoms will coming together, these orbitals 2s and 2p will overlap, and all the electrons will build at some lower levels, and the upper overlap levels will be that they will be just separated out with certain gap. Those are known as band gap. So band gap is the important property of these semiconductors, and whenever we will dope different materials in semiconductors, if we dope like the boron or aluminum, that is they can your holes, the positive type of charges will be increased, those are known as p-type semiconductors, and if we dope or if we add that arsenic or some pentavalent impurities, then electrons will be more numbers, those are known as n-type semiconductors. These are generally in your courses. So p-type and n-type semiconductors, keeping this in mind, we can have a junction, those are known as p-n junctions, and those p-n junction is a very important for us, that is known as rectifier.
Sir, screen dekha jauni screen.
Excuse me, sir.
Dekha jauni screen.
Screen already it is stopped sharing. It is Sukanti madam. Should I stop and again I should share it? Let us, I should stop and I should share again.
It is clearly visible. It is visible.
Now the screen is visible. Now the screen is visible.
Yes, sir,
It is
visible.
audible and visible.
Yes, sir.
Okay, thank you, sir. Thank you. Thank you, sir. Those they cannot see the screens, they may ping out my presented presentations. You may ping out so that the screen can be visible. I hope so. Then in applications, you may by combining those p-type and n-type materials, you have the p-n junctions diodes. Those are known as rectifiers. So to say, it is in day-to-day life we are using in our to charge our mobile phones. So those charging devices are actually known as rectifiers. Similarly, transistors, then field effect transistors, and different classes of logic gates materials are generated from these semiconductors. And without semiconductors, your electronic devices cannot be possible. So, hence, keeping this in mind, your emerging trend of research will demand to have the very important properties of semiconducting materials with lower band gap, lower resistivity, smaller in size, and having some luminescence, high light cycles, and very good responses towards transitions. So then it is another classes of materials known as optical materials. These are also known as semiconducting materials. There I have not mentioned in the list, but these are having some that optical properties. Whenever you will give some light, then there will be some transitions. And from valency band to conduction band, the charged particles will be that they will transit. They will be excited. This is known as photonic excitement. Photon is the particle associated with the light, and hence it is known as photonic excitement. And hence for this kind of property, those materials are known as photonic materials, or so to say optical materials. And these materials have direct band gap property. What is direct band gap? Now you can see the figure that this is known as valence band, and this is known as conduction band. All the holes will be here. All the holes will be collaborated. These are already densified, and here all the electrons will be densified. So now, and all these valence band and conduction band are same energy state. But see the second the figure, their valence band, the maximum peak of valence band and the minimum peak of conduction band, these are at different energy states. So generally optical materials, they exhibit this kind of graph, that is direct band gap property. That means whenever you will give a light, then immediately the charged particles can excite to conduction band, so that you have your transitions, you have your that is electronic communications will be there. So basically light emitting diodes, lasers, drugs, photodiodes are included in this kind of the direct band gap materials or optical materials. Important materials in this category are zinc oxide, gallium arsenide, and materials used for laser emissions. So I have already shown that you can use UV visible spectrometer to have the graph of that is your observance versus energy, and at a certain energy your observance will show a greater transitions and giving a and finding the slope to the x, or finding the point, the tangent to the x-axis. That point is known as the band gap or optical band gap or direct band gap of that material. And whenever that direct band gap is, let us say 3.2 electron volt, that means you have to give the light of 3.2 electron volt. Whenever you will give the light of energy 3.2 electron volt, that materials in that materials will behave as semiconducting materials. So hence you have to enhance its photonic band gap. That means band gap must be reduced, and various lasers materials, lasing materials has to be in the pipeline to research. People are searching and so many materials to give the cheapest lasers with you. Drugs, medicines, light emitting diodes, for a single material with different colors, and transparent colloid solutions and adhesives, so that whenever you are jointing some lenses, okay, like Canada balsam, it has some transparent properties, and various electrical appliances also. And I have cited so many kind of things. See at this diagram, my mouse point, you can see that whenever you will add the zinc oxide with magnesium at 6 percentage, the blue line, and its band gap will be improved. Its band gap is increased. Okay, and as you know that in this microstructures, the different kind of microstructures for zinc oxide, you have a different luminescence property, and in a different luminescence property, you can use that zinc oxide for different electrical applications. So what you need, that you have to go for. That is the basic art of material science. So now you can classify materials with respect to their particle size also. When their particle size beyond 100 nanometer, that is known as bulk phase materials. When your particle size it is less than 100 nanometer, that is known as nanomaterials. I have given, you can see the barium titanate having in bulk phase and in nano phase, and in nano phase is hardness and its all mechanical properties, electrical properties, optical properties are greater with respect to bulk phase. Hence it is better, we must go with the nano phase materials. Now you can classify the nanomaterials with respect to the different dimensions. First of all, you can fabricate nanomaterials by that segmenting a bigger material into very smaller size and smaller size. That is known as top-down approach. And also you can that joint very smaller materials or atomic level of materials to a 100 nanometer range, that is known as bottom-up approach. Keeping this in mind, that when the material dimension is limited to that very point, that is known as quantum dot or clusters or zero D dimension. When material dimension to confined to one axis, x axis or y axis, those are known as one dimensional materials. Example is nanotubes, nanorods, nano air. Similarly, when the nano dimension is confined to some thickness x and y, that is known as two-dimensional nanomaterials, that is known as nanofilms or nano coatings. Similarly, if the nano dimension is confined to three-dimensionals, that is known as polycrystalline nanomaterials and or bulk phase nanomaterials, that you can grow in what applications you need, where you have to apply. In that way, you have to go for the dimensions and you have to go for those techniques to fabricate nanomaterials. So now the important classes of nanomaterials are carbon nanotubes, and having the carbons are bonded such a manner that it form a tube. Similarly, in a bigger tube, a smaller tube, then in a smaller tube, if it will be there, just imagine that is known as multi-walled carbon nanotube, and if it is only single cylinder, that is known as single-walled carbon nanotube. Similarly, if we'll just imagine, if we'll cut the one part of the carbon nanotube, it will be a seed, and that is known as graphene seed. So it is so hard that for a single atomic layer of graphene, it can sustain that more than 1 ton of load. That is so very important emerging classes of materials. Now people are going for it. So now emerging trend of nanomaterials, people have a research for to generate these nanodielectrics, nanomagnetic materials, every kind of materials in nano dimensions. And hence, so nanotechnology is just a blessing for the material scientist. Now we have to go for the another classes of materials. Those are very important classes of materials, that is known as nuclear materials. Here the nuclear materials, this can emit radiations. These are by nature, and different radiations are there. That alpha particle radiations, beta radiations, that is generally electron, and gamma radiations is electromagnetic wave. Okay. And inside it, in a periodic table that I have shown, that the radiation cycle of uraniums and how it will be radiate, and at a certain time interval, and it will be, its mass will be decreased. That is will be signified by its half-life period, that is 0.693 by lambda. The lambda is its rate constant. It can be signifies. So this class, in this kind of materials, you can produce X-ray, lasers, plasma, then gamma radiations, neutron radiations, and these classes of materials are used in reactors to produce electricity. In the emerging resource trend, you have to design this kind of materials with very optimum safety factors, because it may hazard, it may give the hazardous for your health issues also. It is a very, then people are searching how we have to block these radiations, but we have to keep a research on these classes of materials. That is also very important classes of materials. Plasma is also one kind of how you can generate the cathodes and anodes, so that plasma can be generated. Those are also in the classes of nucleus or that radiating materials. Now these are some recent techniques to characterize the materials. For structural, you have to know its particle size, you have to go for X-ray diffractions, electron microscopy, atomic force microscope. Similarly, for mechanical properties like strength, toughness, and yield strength, tensile strength, you have to go for this 3-point bend test, tensile test, etc. To study on thermal properties, glass transfer temperatures, its thermal behaviors, its thermal transitions, you have to go for differential scanning calorimetry, thermogravimetric analysis, and these are some techniques. Similarly, for microstructural analysis, to know the particle size distributions or packing densities, you have to go for scanning electron microscopes, transmission electron microscope. Similarly, there are certain spectroscopic techniques chemistry people are using, also material scientists are using to know Raman spectroscopy for different bond behaviors and different significant functional groups, and UV visible spectrometer for band gap study, X-ray photospectrometry for elemental study, X-ray fluorescence, photoluminescence, Fourier transformation, infrared spectroscopy to know different organic functional groups in the materials, whether some organic functional groups are added or reduced, that you can know from FTIR techniques. And obviously some electric and magnetic properties can be understood from probe methods, electron spin resonance, ESR, and nuclear magnetic resonance properties. These are some photographs of some techniques, X-ray diffractions, scanning electron microscope, and atomic force microscope. Now, all such things the students may visit different institutes, and some of the instruments are also visible in our university, and students can visit our university to know details about it. And I will be happy if the students will come and visit our university to have a better study on this. And now these are some techniques already I have told. Now let us begin with my part 2 presentations, that is an emphasis on polymer composites. That is my research area that I have given my time for this polymer composites from my PhD, MTech, PhDs, and then also nowadays I am continuing with this kind of activities. Now, basic concept of composite materials. What is composite materials? We have to know. Already I have told it. If different classes of materials will be mixed together with clear-cut interface, then the main part of the material, that is known as matrix, which will give you some shape and size, and the other part which will enhance the strength of that material or property of that material in any way, that is known as reinforcement, because it reinforces its properties. And when these classes of materials will coming together with a bed interface, they will not kind of alloys kind of things. They are having certain interface, that is known as composites. For example, concrete, cement plus sand plus rock, that is also composite. Similarly, in brick, soil plus sand, that is also composite. In wood, cellulose plus lignin, those are also composites. So hence, in matrix, can be of metals, can be of polymers, can be of ceramics, different. And in reinforcements, matrix may be of also different types. So now, what reinforcing agent you want in what matrix, that you have to choose with the principle that where I have to use, or what applications I need, and what properties I need in that applications. So in that you have to choose your materials accordingly. Okay. Now these are some components of the composite matrix and reinforcements. Already I have told you what properties matrix should exhibit and what properties that reinforcement should exhibit. That all these things can be understood. So generally reinforcement should have better strength than matrix. So whenever you are using polymer is softer in nature, then you have to choose either metal or ceramics for the reinforcement. So whenever you are choosing metal as a matrix, then higher strength materials than metal is ceramics. You have to choose only ceramics. So in this way, there is a rule of mixture. There is a mixing rule. Okay, keeping that in mind, you have to mix at what optimum percentage, so that that composite materials will give you the optimum strength and desired properties for that component. So now the composites can be classified with respect to different kind of matrices. That may be polymer matrix composite, metal matrix composites, and ceramic matrix composites. I'll put emphasis on polymer matrix composite, and depending on reinforcements, it may be fiber reinforced composite, particulate reinforced composite, and whisker reinforced composites. So now matrix may be metallic like aluminum, magnesium, titanium, or it may be ceramic, silicon carbide, silicon nitride, alumina, zirconia. Polymer matrix may be polymer. So when you are choosing polymer as a matrix, you have to choose that these upper classes of materials are metallic or ceramic materials as their reinforcements. And reinforcements may be in different sizes, like it may be in fibers, it may be in particles, or it may be in short fibers. So polymers, whenever you are choosing polymer as a matrix material, that is known as polymer matrix composites. Then in this case, you have to choose basically a ceramic is a reinforcing materials. So now in that ceramics, you may choose particles or in a fiber form. So basically, I have taken the reinforcements of ceramics in fiber form. Hence, it is known as fiber reinforced polymer composites. That is, so to say, FRP composites. So here, fibers may be taken from glass, maybe carbons, maybe Kevlars or alumina. So different classes of fibers you may fabricate, and you may incorporate in the polymer to have a better properties. Just see the stress strain diagram of a composite material. Just see the blue line, the blue dotted line is for matrix. See how very minimum strength, the cross mark is here, how very lesser strength matrix. And see the reinforcement, the sole reinforcement, how brittle it is. Only it is a stiffer diagram, there is no plastic deformation, so it may break anywhere else. But whenever you are combining these materials of red stress strain diagram and blue stress strain diagram, and it is giving the intermediate stress strain diagram between red and blue, that is the green, and it is the strength is quite decreased, but its ductility that being improved, and that having its yield strength also improved, and with certain plastic deformation points, so that it has some improved properties, then fibers also, then matrix. So that means composites has the improved properties than fibers also, or the reinforcements, or from matrix. So you can see the different classes of material that polymer composites like CFRP, known as carbon fiber reinforced polymer composites. In that I have taken carbon fiber and the polymer as the reinforcements. Similarly, aramid fiber reinforced composites and glass fiber reinforced composites, these have the high strength. Okay, now see the steel. Steel have the strength is here, it is stopped. So, and mild steel, see the red line. So it is better. The peoples are now, they are choosing for composite materials. It is light in weight, and but it has a high strength. So it is better to use composite materials. So, but it is very challenging aspect to fabricate those materials. Now my research area is glass fiber reinforced polymer composites. These are used in various applications like pipelines and in marine applications. Okay, the wind turbines. Okay, the wind blades, and the maintenance of the pipes by GFRP composites wrappings, maintenance of the bridge, maintenance of the boards, okay, in marine and ship bodies, aerospace bodies, and also the insulating sheet of superconducting magnets. All the various kinds of multi-purpose applications of this single material that is known as glass fiber reinforced polymer composites. So these polymer composites have very light in weight and very high corrosion resistant. It will never corrode, greater life cycle, that means having greater fatigue cycle, and non-catastrophic nature of failure, because whenever it will fail, it will give a stretch mark that is known as scratching. So that means it is an indication of failure. In that time, you have to reject the materials. That means it will give the pre-warning of the failure. Then greater toughness, that means so light and so strength. So that means light in weight and it will never break. So that let us consider any material can sustain 50 kg of load. But if you give 51 kg of load, it must not break. So this kind of material, let us say GFRP composites having 50 kg of load sustainability, but it can sustain the up to maximum design stress 70 kg or 80 kg. That means you can increase its load sustainability. Okay, hence this is having greater toughness, easy of fabrications and low maintenance cost. But the basic problem is that these polymer composites are, so to say, fiber and force polymer composites. Their mechanical properties and thermal properties can decrease in moisture environment or high temperature environment. And curing is a very big problem with us. It is very a crucial problem for us. We cannot achieve ultimate or optimum curing for that polymer, so that that material cannot be hardened up to our desired extent. Presence of voids and selection of suitable polymers or suitable fibers for different classes of materials. Keeping this in mind, I have fabricated these materials and exposed to a humid atmosphere, that is water immersion, and a environment where moisture is there with high temperatures. Okay, so in that temperature, I expected these properties like plasticization, swelling, and hydrolysis, so that polymer can be deteriorated. So in this kind, I have exposed the materials to these environments, and I have studied its mechanical property, thermal property, and microstructural property. See, moisture gain will be improved, and after certain days of moisture, it is having a plateau trend. That means constant trend, so that up to that level of moisture, to that level of the decrease of strength can be tolerated up to that design stress levels. Hence, its ILSS, so to say, interlaminar shear strength being that decrease. Why that is shear strength? Because I have taken glass fibers and polymers in layer based. So when I have given the load, those layers will be having relative motion. In that relative motion, there is a shearing. The lower part is having tensile and the upper part is having compressive loads. Hence, those are having shearing kind of loads. So I have to know its resistance to shearing, that is known as the interlaminar, or among the layers, up to how much shearing strength should be sustained, that is known as interlaminar shear strength. It is a crucial parameter for FRP composite, and it is decreased up to certain extent, and up to that design stage, you have to fabricate your composite materials so that it can be applied in aerospace or in applications where moisture is there. Similarly, thermal properties decrease up to certain percentage, and in that level of design stage, that level of thermal glass transition temperatures, you have to go for its fabrications. And its spectrographs, you can see that how materials being break by fiber breaking, polymer crashing, and fibers being pulled out. So in that way, your microstructures can be understood. Similarly, I have fabricated glass fiber and polymer composites and exposed to seawater. Why seawater? Because in marine environments, glass fiber reinforced polymer composites will never corrode. If it will never corrode, it can be used in so many years in sea environment or immersed in sea environment. So hence, keeping this in mind, I have taken that this GFRP or glass fiber enforced polymer, and in polymer I have taken epoxy resin as a polymer, and for years, up to 12 months I have exposed in a room temperature, and I have studied for moisture gain, its mechanical properties, its thermal properties, and its elemental properties, and its microstructural properties. So you can see the moisture gain being improved, and at a certain level of days it is being constant, and after which it is again improved. That means I have to use the material in this durations. So beyond these durations I cannot use it. Okay, so that is a very small materials I have fabricated. But if I will give its dimension, I will improve, its layer I will increase, then its sustainability capacity will increase, maybe up to 5 years or 6 years or maybe up to 10 years. Similarly, its interlaminar shear strength also decrease up to 23% after 1 year. That means I have to keep in mind its design stress, so that I will improve its design stress up to 23%, so that materials can be used in seawater with sustainable performance. And I have studied the glass transition temperature by differential scanning calorimetry. After 1 year, that temperature is 88.21 degrees centigrade from 1 to 20 degrees centigrade. That means up to 80 degrees centigrade of that material can sustain in sea. Okay, I can use it up to 1 year. So now I have choose for the elemental study. In that elemental study, that I can see that up to 1 year sodium penetrating more into the materials, and by which it is depositing across the interface at that material, so that its sodium percentage at the surface will be greater, and it is never allowing the moisture. So after 1 year, it is giving sustainable performance. So now scanning electron microscope spectrographs showing after 1 year that you can see the fiber will be burnt, but matrix will be cracked. That means it is so stupend, so strong that all the loads has been transferred to the matrix, so that matrix will be cracked, but fibers are not have a single fractures or single crack or single that crack breakage you have seen. That means the material can sustain in the seawater in very with a very effective sense. So now this glass fiber reinforced polymer composites with a very excellent corrosion resistance, it can be used as piping material, that pipes, so that seawater can run inside it. It can flow inside it. So that hence I have fabricated a glass fiber reinforced epoxy pipe by this method. That I have taken a stainless steel pipe, then the glass fibers I have wounded over, then applied the polymers, then I have hardened it. After that, these materials you can see in the diagram, I have taken some that this tube is arranged in this experimental arrangement to run seawater in the lab for 1 year continuously, and I have inserted a electric bulb inside it up to 50 to 60 degrees centigrade, so that in the daytime its temperature being improved, and in the night time its temperature being reduced. Why I have did this? Because in deserts and nearer to sea environments, the peoples must have a desalination plant, and they must have to procure the seawater from this or procure the drinking water from the sea, and they will desalinate it. Again, they will recover that desalinated water for the drinking purpose. How they could do this? Priorly, they could do this by steel pipes or metallic pipes, but generally after 1 year those metal pipes being corroded. Hence, these materials will never corrode. So keeping this in mind, I have fabricated this kind of materials with pipes and allowed the running of seawater inside it for 1 year. Then I have studied its moisture behavior and its mechanical properties, its thermal properties, that is to know the glass transition temperature, and its elemental properties, and scanning electron spectrographs, or that is Polumer modes. See that up to 2 months that moisture gain is improved. From 2 months to 10 months moisture gain is very reduced. That means I can use these pipes with a very sustainable experience. Then up to 10 to 12 months that its moisture gain is increased. But in that level, though the moisture gain is improved, see the ILSS being so constant from 8 months to 12 months. That means it is stagnant. So from that, I have already studied, the graph is not extrapolated here. That means its strength not being decreased, and it is having an increase in trend. That means I can use beyond 1 year also. And its glass transition temperature, see, it is having an approximate increasing trend from 2 months to 12 months. See, 75.7 to 93.3, it is improved. That means its thermal properties also improved. Now, why it is improved? Generally, in a moisture, properties should be decreased, but here it is improved, but in a very slow manner, in a very slow continuous manner. That is known as in a very low quantitative aspect. So hence I have gone for elemental mappings of those surface of the pipes. I can see the salts, the calcium, magnesium, and potassium, sodium, calcium being penetrated more, and your sodium being penetrated very less. And I have gone for the Fourier transformation infrared spectroscopy. At the 1 year, I can see some additional elements that of amide or aromatic ketones and carbonyl groups are forming due to some additional polymeric or some organic functional compounds are forming, and those are packing inside it and giving strength to the materials. Similarly, by XPS analysis, I can see that how the salts and how much the salts with the amounts they will be associated with. So hence I have studied the mechanisms by taking those seawater, the used seawater, and have a fluorescence study that I have then concluded with the aspect that sodium at a great extent that will be deposited at the surface, and there will be some bacteria, those are forming in favor of sodium, and sodium is used as the nutrients for these materials, and these are locking these bacteria so that bacteria will lock these salts and more number of salts will be blocked at the surface, so that after 1 year no moisture is going into it, and hence its mechanical properties being maintained or being stagnant, hence we can use it forever or after 1 year. And you can see that after 1 year all the fibers being bonded, and all these bonded fibers giving provides the optimum or that best strength to the materials so that it can be used. Hence this is published in a very reputed journals of Composite Communications in 2020 of this year. And now these glass fiber reinforced composites, this can be used as electrical and thermal insulators in superconducting materials. Keeping this in mind, I have exposed these materials, fabricated first, then exposed these materials to gamma irradiations, and I have conducted this experiment in BARC, Bhabha Atomic Research Center, Mumbai, for low intensity and high intensity. Then at low intensity, the strength being decreased, and in high intensity its strength being improved. Now from that I have concluded that maybe at high intensity doses that polymer may be cured up to desired extent so that its strength being improved. And similarly, their glass tension temperatures at high intensity doses are greater than from low intensity doses, and the composite that exhibits the color change with a very good strength. Then I have gone for FTIR analysis, Fourier transformation, infrared spectroscopy, and in that at a certain wavelength, wave number zone, that some additional oligomers. Oligomers means the small molecular weight polymers, those are known as oligomers. These are being formed with amides and ketone groups, and these are helping a lot for the curing purposes. Hence, at the high intensity dose, you can see that all the fibers are getting together and fractures are being less. But in low intensity dose, you can see fibers getting delaminated and matrix getting failure. Now, these components are also very important in different aspects of achieving ultimate curing strength. So hence, with respect to different curing methods like electron beam curings, gamma irradiations, ultraviolet curings, microwave curings, and plasma curings, from different researchers, I have gone for plasma curings. In this experiment has been conducted in C.V. Raman Global University, and I have exposed these materials up to 30 minutes of plasma irradiations, and I can see that its interlaminar shear strength being improved considerably with a very limited interval of time, that I can gain its strength up to around a 20% of increase in the 30 minutes of plasma exposures. Hence, that at a 25 minutes of plasma exposure, I can see its glass tension temperatures is increased considerably. Hence, you can see that at a plasma exposure of 25 minutes, the failures being less, no failures can be visible, only matrix crashing and fiber matrix rebonding. And that thermogravimetric analysis can see that at a 25 minutes maximum that weight percentage, that weight loss will be there, and in that case I can claim that with respect, if I give plasma radiations to these composites, glass fiber and polymer composites, this strength being enormously being used. Similarly, I have designed these composites and exposed just in a normal environment, like at the rooftop. and for some up to 3 months. Then up to 3 months, I can see up to 60 days that its moisture gain will be increased, but at a certain that at a 30 to 40 days, its strength being that it's a maximum and it is increased for different volume fractions of fibers. Then I can conclude with the remark that these composites that also sustain in our natural environmental exposures, where very crucial moisture exposures and temperature fluctuations is there. And this experiment is carried out in Bhubaneswar. The Google map image is also attached here. And at the optimum percentage of the fibers, you can see that failures being laced and fibers being stacked together, and their properties being enhanced. So now, keeping this in mind, again I wanted to improve its property with respect to the additional curing techniques. Then I have added some nanomaterials like graphene oxides up to 0.05%, which is very less compared to the overall weight of the materials, and I can see 20% of increase in weight, and the glass tension temperatures will be increased up to 1.88%. But whenever I expose these materials to sea water, it's that in presence of graphene oxide, the strength decreases only 15.27%, but in strength decrement is only that 35%, 24.48%, but without graphene oxide the strength decreases 35%. See how sustainability being improved with addition of 0.05% of graphene oxide. So very crucial. Hence this is being published in a very reputed journal, and that addition of 0.05% of graphene oxide, that material glass fiber reinforced polymer composites, I have exposed to plasma radiations, that in presence of graphene oxide, its properties being improved to 4.22%. That means here I can control the properties of the composites by incorporating nanomaterials, or also by suitably considering their curing techniques. So now all these are my research area. I have completed with so many research things are there, but time is a factor for us. So hence I should not extend all these talks. So let me to tell all the glimpse of my academics, or that Sridhar sir has already told my academic qualifications from PhD and those from BSc to PhDs. And now one of the PhD students is continuing with myself, and I have already guided 13 of MSc thesis, and my research area belongs to composite materials, polymer composites, environmental sustainability of FRP composites. Anyone, those physics, chemistry students may collaborate with myself to have a very good research in it. These are my awards and achievements I have gained. This is my Google Scholar screenshots for the research papers published, and these are the some screenshots of my important papers, some high impact factor papers I have published in some very reputed Scopus and Web of Science journals. And these experimental expertise I gained, anyone can take the help of me, they may intimate, and these are my software skills. I may collaborate and I may contribute for your interest. And this I have got best oral presentations in a conference, international conference in 2018. This is the screenshot I have taken. These are my research collaborators, and I have associated with so many reputed institutes like NIT Rourkela, CGCRI Kolkata, IIT Kanpur, and many more. And I have also associated with the MSME industry in Noyagarh, Bhilamat, and the founder of Bhilamat is Dr. Ramesh Chandra Biswal, PhD from IIT Kharagpur. And who can collaborate with myself? Well, all the faculties, researchers, industry persons, and those are they may interest in polymer composites or their properties, or some curings, or nanomaterials, or incorporation of nanomaterials in polymer composites or nano hybrid composites. Those interested peoples, they can collaborate with myself. I wish to collaborate with the peoples who can create man-machine interface with optical fiber sensors and can create low-cost DC plasma unit with hands-on experiments and associated with nanophotonics or energy harvesting applications. I used to collaborate with themselves. These are some glimpses of photographs. I visited so many institutes: IIT Madras, IIT Kharagpur, IIT Kanpur, College of Engineering Pune, and BRC Mumbai, and IIT Bhubaneswar, NIJAS, IMMT Bhubaneswar, and of course my alma mater NIT Rourkela. And this is the material science lab that I have designed in C.V. Raman Global University. And these are some glimpses of photographs in electronic and printed media. And at last I must say thank you for your patience hearings. Thank you.
Thank you very much, sir, for such insightful and elaborate and brilliant presentation. It is really amazing. And now I request our students and invite from them questions. And you see, so after such a brilliant presentation by sir and such elaborate presentation, you must have some questions in mind, particularly physics students and physics faculties. I invite you to ask questions. So any one of our from our department of physics, any student, you ask questions to sir. Yes, our physics students, you may ask questions. So a seminar is incomplete without interactive session. So I invite our physics students. Sir, Sridhar sir, you can ask any of your physics students to ask questions. There are so brilliant students in our college. There are Jyoti Prakash or some other students. I think they will ask questions. Now, you mute yourself. Nobody should make any noise, and anyone who wants to ask questions may ask. Any
Please
questions?
don't be hesitant to ask questions. That's a separate matter. I may answer or not, and I can answer or not answer. Don't hesitate. There must be some queries, not doubts. There must be some queries in your mind. You may ask.
Not only students, but other faculties of physics can ask, because sir is ready for answering questions, and you have seen how nicely he has presented his paper. So, sir, unmute karandu. Sir. Yeah.
Anand sir.
Yes, sir.
Please explain. Our body is made of elements. Our protoplasm, our cell, all these are made up of elements. So, are we belongs to the material science?
Yes, of course, sir. We belongs to material science. But question is that what class of material science we must belong to. So there are different that materials belongs to biomaterials. And as you know that our teeth is a dental material made up of ceramics. That means that is also a material. And you can know that at a different aspect of our body, different bone strength is also there. Like there are some cartilaginous, that is also very soft phase of ceramics, or those can be said as polymers and ceramics, and things are there. So basically those are also materials or biomaterials, we can go for it. And but I have not focused in that, but these are materials. Everything you can see, those are materials.
Thank you, sir.
Any other question from anyone? Any other question?
Hello, sir.
Sir,
Please, categorize the how to in which way the students will be inspired for research work or to take physics or material science as their career. Just simplify this.
That physics or chemistry students, they can collaboratively or in interdisciplinary approach, they can go for the research in material science, because material science is the mixing of the theories we have from physics and chemistries. So after BSc, they can go for MSc in chemistry or MSc in physics or MSc in material science and somewhere else. And those physics and chemistry peoples, they can qualify GATE or NEET, and after NEET they can apply some the institutes of national importance, or so many state universities also we have in North Odisha University, material sciences there. In our university in physics, we have also material science labs also there. They can apply for their PhDs, and they can come, and at that moment they have to choose in what material I have to continue with my research. It may be metals or ceramics or composites or nanomaterials, their interest and their applicability, and in that time which materials are having some demands. So in that way they have to choose, and we the faculties must guide, to give certain insight for them. So many institutes are creating those guidelines and those entrepreneurship programs, that creating seminars for them. But basically for physics and chemistry teachers, the faculties are enough to give the guidance for them. They have to be very strong in theories, basically in solid state physics, statistical physics, quantum physics, and similarly in chemistry, spectroscopy and organic, inorganic, physical chemistry. They must be so strong to come this research area in material science.
Thank you.
So any
Thank
more
you, sir.
questions? Any more questions from students or faculty? Anyone? Now I think there are so many sirs and madams, and they can ask questions.
Hello,
Now
sir.
please,
Hello,
yes.
Yes.
sir. Myself, Manoj Kumar Mahalik.
Huh?
I am from social science department.
Yes.
And sir, would you agree with me? Matter is motion in character. We can classify matter into two types: vital motion and voluntary motion.
Yes.
Because man itself is a matter.
Yes.
Suppose blood circulation. Blood
Yes.
circulation is the example of a vital motion.
Yes.
When we are speaking, we are teaching to the students, it is the example of a voluntary motion.
Yes.
Voluntary motion gets impacted by outside, but
Yes.
a vital motion gets impacted by inside.
Yes.
So, since I am from social science department, I would like to say Galileo Galilei and Thomas Hobbes. Galileo Galilei speaks that we have to simplify a simple matter into compound matter. Matter.
Yes.
We have to clarify the mathematics problems, or we can resolve mathematics geometry problems through the materialistic way, through the
Yes.
simple making question, or making into very compound manner. We can resolve the problems. But here my question is that, would you think the matter is dynamic character? Whether
Yes.
would you think matter, some to the extent matter will be stable in character or stagnant in character?
Good afternoon,
Suppose,
sir and ma'am. Sir,
hello.
I have a question. When you took your samples at on your rooftop
Sir has not
for
completed his question.
to get some
Hello.
result,
Please.
then
Please.
after
Hello.
from there
Hello.
you get
Manoranjan Mishra.
the call blowing at your
Manoranjan Mishra, you can
Manoranjan
ask your
Mishra,
question.
sir has not completed his question. Let him to complete, and I have to give the response. After which you can ask your question.
So, sir, so in this context, I would like to say, Karl Marx, when he said that whether outside gets impacted or not, but that does not matter. The matter is that inner contradiction of human being.
Yes.
Man has to fight with inner self. Suppose, for
Yes.
example, a person suffers from a disease. A person suffers from fever. He has to fight with this fever. Then automatically he will be cured. But when we are speaking about the matter, would you think sometimes matter takes rest? When we are speaking matter is dynamic, would you think to the extent matter gets rest?
This concept is originated from the concept of inertia. So in physics, it's a very familiar term, and it is, of course, it is well known to every branch of peoples, that is inertia. So with respect to inertia, and if it is not dynamic with respect to my frame, it is dynamic with respect to others' frames. So hence, it cannot be understood. It is completely dynamic with respect to any frame. So hence, we can say it is relativistic. So in that way, you can that aspect may be claimed.
Yes, sir. Thank you, sir. Thank you, sir.
Thank you.
Okay. Now, Manoranjan Mishra.
Manoranjan Mishra, you can ask.
Ask. Hello, Manoranjan Mishra. Unmute yourself and ask your question. Manoranjan Mishra. Manoranjan Mishra, ask your question. Are you there, Manoranjan Mishra?
So now my ask.
Yeah. Now you can ask your question.
Sir, how can we treat materials with nucleus and nuclear materials? That is nucleons.
Can you repeat this question?
Sir, how can we treat materials with nucleons or nucleus materials?
Nucleons in nuclear materials.
No, sir. Nucleus in nuclear materials. Inside the nuclear materials. That is nucleon.
Inside the nuclear materials, how can we keep our materials?
How can treat the material with the nuclear material? What is the relation between them?
I'm not getting your question completely. That you want to ask that how can we keep the materials in nucleus, or what the relation between nucleus or nuclear materials? Is it?
No, sir. What is the relation between the material and the nuclear material?
The relation between nuclear materials is also one kind of materials. Those radiate spontaneously. That sometimes you have seen that materials are providing some lights. Those are also nuclear materials spontaneously. And some materials will provide some energy. Those are also giving some radiations. Similarly, in the basic example of nuclear material is uranium. Whenever you will give a neutron that bombardment, then that uranium giving a high electromagnetic radiations or some high energy, and those high energy can kill, and it can explosion. So hence there are so many techniques to control it, and the control type of things. By controlling, we can acquire those energy to provide the electrical things. Nuclear material is one class of materials. It is, we cannot formulate any materials to nuclear materials. These are in general available.
Yes, sir. If nuclear material is vibrated, then can it forcefully vibrated the whole of the material, like the massive?
No. If nuclear materials will be vibrated, it cannot forcefully vibrate whole of the materials. It only radiates energy. It only radiates the energy. But if that material belongs to piezoelectric class, that when piezoelectric class.
Sir, that material is constitute of that the nuclear material. Sir, for why when it is vibrated, why can't it the whole material is not vibrated?
Due to that energy, when a massive energy is coming, that energy giving the impact, that hence the system getting vibrated. But the material is not vibrated. The vibration is not the cause due to the material itself. It is the cause due to the high energy it is providing, and that high energy in that is, we can say that nuclear energy to mechanical energy conversions. In that conversions, entropy being increased and the system getting vibrated, but the material not getting vibrated.
Sir, actually, our day-to-day life, the materials which we see that are in not vibrated state.
No, not vibrated, but there are some materials in general that is I have not included in my slides. Those are not known as piezoelectric materials. Just you can put a mechanical stress, then it is vibrating. Some electrical energies you can generate. Those are known as energy harvesting materials. So
Sir,
those are vibrating inside it. So there are particular class of materials that can be vibrating in nature. But with respect to that, you have to provide some energy in it so that it can give you the vibrations.
Sir, in your day-to-day life, we have temperatures and lights. We can't get them out. So when it strikes on the surface of the material, then it gives
It's a very good question. It's a very good question that we are providing energy and continuously we are providing lights, temperature in a material, but that must have to be vibrated. See, I do not know whether it belongs to which branch, physics or chemistry. Physics. In physics, there is a subject known as quantum mechanics. And as you know that a very sufficient amount of energy can penetrate through any wall, so that it can penetrate through the wall and go up. Now, whatever radiations in light or in temperature day-to-day life we are providing in the wall or say wood or any furniture, those are not sufficient. These are not crossing the threshold. These are not crossing its barrier limit. Hence, these are incapable enough to cause any kind of response in it. Okay, but let us say you will give a high energy neutron radiations in your that wall, it will vibrate. Okay,
sir, if we got this such type of small material from the highly from the biggest material, and we strike that lights and temperature which we get from the day-to-day life, then can this material will vibrate?
No, materials is not vibrating. See, material composed of smaller and smaller units, molecules and atoms. Inside it, what is going on? Let us say in our house, we are quarreling also and we are also gossiping. So whenever we are quarreling, is our house is vibrating? No. But seems as if our house is vibrating. Similarly, in material, there are so many molecules or lattice arrangements. Whenever a light or any sufficient amount of radiations is penetrating inside it, those are vibrating. Those vibrations are known as phonon vibrations. I think you have known about this term.
Yes, sir. Sound particle.
Phonon vibrations. Phonon is the wave of the vibrations of the lattice arrangements. When these vibrations are sufficient enough to cross the lattice vibrations itself, then the whole materials will vibrate. So don't think that materials is vibrating. Their subatomic particles are vibrating, or crystals are vibrating.
Sir, I think that the material will vibrating, but it is not enough to count us. But we don't count it.
See, we are not counting it. We are just recording the response.
Yes, sir. Okay. Yes, sir.
So that response is not visible to us, whether in form of itox or in form of any vision. Okay.
Sir, we don't say that it is not vibrating. It is vibrating, but we don't record it.
Material is not vibrating. I am again repeatedly saying their subunit particles are vibrating. Okay, but these are not sufficient enough to cross its threshold or cross its barrier, so that the overall material can show the overall vibrations. Getting your, I think?
Yes, sir. Yes, sir.
Okay.
So now I invite Manoranjan Mishra. Manoranjan Mishra, you have raised a hand and you are asking while sir was asking. So now you can ask your question if you want, or I will shift to vote of thanks. Anyone? Manoranjan?
Thank you, ma'am. Good afternoon, everyone. I am Manoranjan. Sir, my question is, when we're striking some light or any sorts of energy to a surface, if the given energy exceeds the threshold energy, then will it vibrate?
See, the when the you are providing the light to any material, the let us say threshold being crossed. So
Yeah.
then which will vibrate? That light of energy, let us say h nu, its frequency nu and its energy you multiplied that Planck's constant h nu, it is triggered to have the vibration. Then which will vibrate? The atoms in the lattice will vibrate. Okay, and that will give you the phonons. Then all the phonon waves they will superpose. Then after superpositions there will be some resonance. Then all the that all resonating waves when will completely match all the resonating waves at the same frequency they have to vibrate. Then only your material will show the overall vibrations you can see. Getting my point? Like a seismic wave, your seismic wave, earthquake wave. These are at the center, at the epicenter. These are vibrating at the same frequency, and there will be some resonance, and the tectonic plates are vibrating. Not molecules, atoms, lattice, as well as all the materials and all the tectonic plates. These are also vibrating, and you are also getting vibrating. Getting my point? So that thing is also necessary. You have to reach that phonon resonance. Until unless you will never cross that phonon resonance, material will never show you. Maybe it is vibrating, but you cannot see it. But it will never show you that response that you can feel the material is vibrating.
Sir, I have another question, sir.
Yes.
Sir, you illustrated an example of a room when we are gossiping among each other. Then will it vibrate the whole house?
No,
No.
it will not. But
No,
it will be so louder. Let us say I will speak very louder, louder to louder to
sir,
louder, and
sir, my
someone is
question is that.
from
So,
that room, sound is coming. That means he is feeling the sound from a single room. So as if like the room is vibrating, but they are telling not like that room is vibrating.
sir, then as you said, then if we say it louder, then it will vibrate the whole house. Is that
No,
right?
no, house is not vibrating. House cannot vibrate. Okay, it has to vibrate with its certain base and its tectonic plates has to vibrate. Okay, scientifically it is not vibrating. It is psychologically vibrating. Okay.
So
Thank you, sir.
now Trupti Misra. Hello, Trupti. Are you there? You want to ask a question? You can ask.
Yes, ma'am. Yes, ma'am. Sir, good afternoon, sir.
Yes.
Sir, my question is that you said polymer composite. That polymer and composite are two different things, or it's one thing?
Polymer is a different materials. Polymer composite is different materials. Polymer is a sole class of only polymers only. But in polymer composites, you have to take polymer along with another class of materials like ceramics or metals. Basically, you may take ceramics. So polymer plus another class of materials are intermixed together to have polymer composites. Hence, polymers and polymer composites are different.
So normally we say that PBDB is a polymer ceramic composite or barium titanate. These are sir polymer
Barium,
or
PBDB is a polymer, barium titanate is a ceramic. Then whenever you like PBDF with barium titanate, that is known as polymer composite.
yes,
So
sir.
you are in that case barium titanate is the enhancer or enforcement. That barium titanate gives the dielectric property, improves dielectric and all the electrical properties, and PBDF giving the shape of the materials and overall that dielectrics properties and electrical properties, and it is being improved for different classes of materials.
Sir, one more question. Sir, why the hard phase of polymer matrix is seen dark in electron microscopy?
And can you repeat this?
Sir, why the hard phase of polymer matrix is seen dark in electron microscopy?
If it is seen dark in electron microscopy, that is in secondary mode, secondary electron mode. You have to go for backscattered mode. So why it is dark? Because the polymer is insulating in nature. The electron is not penetrating inside it. When electron should penetrate and then it will reflect, then only you can see the image. So in that case, you have to give a coatings, some conductive coatings on it, so that electron will reach at its surface and it will getting reflected. You can see a brighter kind of image. So if it is not possible, then you have to go for backscattered mode.
Yes, sir. Okay, sir.
Thank you.
Thank you, sir.
Okay. Now it is time for vote of thanks. This is the last program of our webinar. Now, after listening to Sir and such a brilliant presentation by him, I am really impressed. Though I belong to literature and I have no such great inkling into the topic that was discussed. Still, I could understand something because of that nice presentation. Thank you, sir, very much for this presentation and being so energetic while and involving while presenting your slides. So I could find it very nice and very beneficial, quite beneficial for the students and faculties. Now, for the support of our principal, sir, who has always attended us with patience and supported us for and guided us for presenting or conducting such webinars, I owe him my gratitude. I am thankful to Sridhar Panda, sir, whose initiative has made me organize this webinar. I could see a lot of interest in him and he could not handle the techniques, so I helped him. But it is solely for his interest, his initiatives and his cooperation that I have done this. So I am thankful to all my students who have raised questions, all the participants and all the dignitaries. So now, shall I end the meeting? Principal sir, shall I end the meeting or anything you want to say?
Yes.
So, sir, to our resource person, sir, this recording I will send you through your mail, and you will just ask for a permission because this is from the G Suite mail. So, after getting the permission, you are getting access to the recording, and I will also upload it to my YouTube channel, and I will give you the link. Thank you, sir.
Thank you, madam. Thank you.
Thank you.
Take a photograph, madam. Take a photograph.
Photograph, yes. I'm asking my student Ankit. Ankit, you take a screenshot. Or I am taking my mobile. Yeah, I am taking a photo. Yes, sir.
Yeah, thank you, Anand sir.
Thank you, sir.
Please, when come to the BHADRAK, please visit our college.
Definitely, sir. I will be.
Welcome.
Sir, namaste, sir. Namaste. Now, goodbye to all. I am ending the meeting.
Thank you. Thank you.